Hey folks, welcome back to the series where we're learning about AML and GPU from an SRE perspective. So the topic for today is video RAM and ECC. So let's talk about video RAM first, right? I used to think it was virtual RAM first. I don't know why I thought that, but it's a completely different thing. So let's see what a video RAM spec looks like when you try to provision a GPU, right? So I'm in vast.ai, and when I look at my console, I see that GPU has, 4 RTX 4090 model, has 24 gigs of VRAM. It has 900.8 Gbps as its bandwidth. That's one example. So at the very top, I have 24 gigs again, and then my bandwidth is 899, and that's my RAM, right? So that's per GPU RAM. Okay, so it depends on how many GPUs I have here. And then the other thing here you see is that the system RAM is 516 gigs. Notice the size difference, right? That is quite important. We'll come back to this later on. And then notice the bandwidth as well, right? That bandwidth is really, really high. So going back to this drawing here, so we see that, like VRAM sits on the graphics card, whereas our traditional RAM sits on the motherboard, right? VRAM is dedicated to GPU for graphics and compute. Our, RAM is general purpose memory for CPU. It has very high bandwidth to feed thousands of cores in parallel. So, GPUs are very heavy in parallel processing. Whereas our normal RAM has low bandwidth, but it's optimized for CPU workload. So coming back to the bandwidth point again, we see really high number of bandwidth, right? So going back to this diagram here, I kind of want to talk about the flow of data a little bit as well. So what happens is you might, you have your data initially in some form of storage device, right? Let's imagine an SSD. You have your images, you have your data sets, everything stored there. So that data needs to be processed into RAM by CPU, right? So CPU helps, to load all that data up into the RAM. So once that data is loaded in RAM, then that data is transferred from normal RAM to VRAM, right? So two ways to transfer that data, as I understand now. One is PCIe, which is the more traditional way, and then there's NVLink, which is the new way developed by NVIDIA, which is more faster and it's more geared towards GPU use case. So once we have the data in our VRAM, so now GPU can access that data much faster, right? Because the bandwidth is just really, really high. And we know GPU does parallel processing, in a really extensive way. So it needs that amount of data. So, and that problem is solved by VRAM, right? So if we didn't have VRAM, if we only had a RAM, like it would just not have that bandwidth, right? And your GPU will be idle. It won't have enough data to process, because by the time RAM sends the data, GPU will be done instantly, and it will still be waiting for more data. I think the better analogy to understand here would be, think like a two-lane highway, right? So, RAM is sending the data to VRAM using a two-lane highway. Once VRAM has all that data, then VRAM provides 12-lane highways, for example. So now when GPU needs all the data, it can use this 12 lanes to access it. If we only had RAM, all of this data that you have here will be transported using only these two lanes, right? So your GPU is super quick, like the amount of data coming in is just not enough for your GPU. Whereas with VRAM, with that bandwidth, you can keep your GPU busy. So having the right VRAM is quite important to not have an ideal GPU, because when you pay for GPU, you pay expensive price, right? So to ensure how my GPU does not stay idle, in one way would be to ensure that you have enough VRAM that can keep your GPU busy, right? So while we talk about VRAM, there's one important concept that we need to understand. It's called error checking code. So I'll actually put a link here where Stanford did a research about hard data on soft errors and a large scale assessment of real world error rates in GPU. So you can get into the details about the study, but have a brief summary here about what is error checking code, what happens, and so on. So data corruption can happen due to cosmic radiation or electrical noise in the memory world. So because of those corruption, your one bit might flip, right? So in this example, we see that this is a binary for 179. Due to some electrical noise, one bit flips, right? So now let's say that bit flipped and then it became 0 instead of 1 now. So that's a binary for 177. And then GPU reads 177 instead of 179, because we have seen here that data is transferred by VRAM to GPU, right? So this is where the flip happened. GPU has no idea, right? It does not know that the flip happened. It'll just, pull the data and do its thing. So GPU reads 177 instead of 179. No one tells you. Wrong value will be processed. So what are the consequences, or what are the results from this, right? You might see a slightly wrong pixel in an image. You might have a wrong weight in your ML model that might compound over time. So this is also called as a silent data corruption. And it's very important to have VRAM that has error checking code as a feature. If you don't have that, then you can't run your production workload with a VRAM like that, because these kind of errors will be completely missed. Like silent data corruption will happen, and then you will get wrong results, right? So that's one spec to keep an eye on. So once you have a VRAM that has ECC enabled, so we can detect these kind of errors, right? So how does that happen? So what ECC VRAM does is that it'll add an extra parity bit, and these bits will let these bits detect and correct the hardware errors, right? So there are two ways of correction and detection, let's say. So the first one is like single bit error corrected. So what parity bit does is that it'll implement the logic. This is a very simple example. Like the logic implementation behind is much deeper and much more complicated. But just for understanding in a simple way, it might count something like, okay, there are 5 ones here and there are 3 zeros here, right? And what happens is, due to some electrical noise, it flips the last bit. So that ends up becoming 0, right? So now our parity check will detect that, like the number of ones and zeros does not match, right? Now I have 1, 2, 3, 4 ones, where it should be 5 ones and 3 zeros. So it'll detect that and it'll fix it, right? It'll say that, okay, yep, that bit changed. Let me flip it back to 1. So that's error solved. But then there's another case where it's called double bit error detected, right? So notice this terminology: single bit error corrected, double bit error detected, right? So what happens is, parity bit might use a similar logic as we discussed before, count the number of ones and zeros. Electrical noise will flip the last 2 bits. So in this case, the last 2 bits went to zeros. So now parity check can detect that the bits are flipped. So it's not 1 anymore, it's 2 zeros, right? But it cannot identify where the bits flipped, right? So in this case, what happens is the GPU driver raises an error called uncorrectable ECC error. In this situation, your job might crash, GPU might reset, but at least you won't continue silently with the bad data, which might have bigger problems, right? So, if it's a single bit error, it gets corrected itself with ECC, with the parity bit logic. If it's a double bit error, then it's detected, it's not corrected, right? So how can we get around this problem? So there's one way to get around this problem, and the solution is checkpoint. So periodically save the workload state. And, a couple of states that you might want to save would be model weights, training programs, optimizer states. And if a training job crashes, then we can restart from the last checkpoint. And I think one thing to consider here would be the data center grade GPUs must have ECC VRAM. So that is a very important point to notice. So, to sum things up, right, I think you can say that VRAM is the guy that feeds data to GPU. It has really high number of bandwidth. That's why, GPUs use VRAMs to talk efficiently. If you want to keep your GPU busy, make sure you have a good VRAM and enough data to keep your GPU busy, absolutely. And then for production grade GPU machines, you need VRAMs that has ECC enabled. If you don't have that, then you might silently corrupt your data and you won't even know. And with ECC, there are 2 kind of examples, right? There are 2 kind of errors. So one would be single bit error corrected. If a single bit flips with the parity bit logic, it can be corrected, no corruption at all, no issues. But with a double bit error, when 2 bits flipped, it will be detected, but it can't be corrected, right? So at that stage, your job will crash, but your GPU might reset. But if you take checkpoints of your job, you can restart from the last job, no need to restart from scratch. At least you don't move ahead with the wrong data. And then we saw an example here where we have the bandwidth and then the size of VRAMs being quite smaller to traditional system RAMs. And I hope you guys enjoy this video, and thank you for watching.